Okay, so I hope you've heard of HETDEX. Have you heard of HETDEX? So this is the hobby, This is the Hobby Arborlee Telescope, a dark energy experiment. Okay, we are taking one of the largest telescopes in the world. We have already installed the largest spectroscopic instrument in the world, and we're going to increase it by another factor of 2.5. We're going to do one of the largest surveys in the world that has been done on the sky. And we're going to use the most powerful computer, one of the most powerful computers on Earth as well. And we're going to put those things together, and we are going to kick butt completely. This is, and we are going after dark energy. So this is one of the most important mysteries in science and astronomy right now. It has to do with how the universe, why the universe is expanding the way it is. We don't understand it. I'll talk a little bit about that. But let me just start out a little bit with the experiment. And just to set the scale, here is a schematic of the telescope and the various parts of the telescope. And we basically, so it's a $42 million experiment. We are almost done with the building. It's working now. We've been taking data for about a year. I'll show you some of the data. It's about a 4-year experiment from now, and it's looking fantastic right now. So let me start out with the story, and just to set it, I'm going to put some phenomenal eye candy in the background that I just love. And so this is one of the greatest images I have seen, and I want to talk about this. So I want to talk about a photon, the story of a photon. You've probably heard this story, but there are certain aspects I want to get across. Okay, so imagine a galaxy far, quite a distance away, I'm sorry. So there's a galaxy maybe 10 billion years ago. When the galaxies were very young in the universe, we did not have all of the periodic table that Dr. Wheeler showed you earlier. We only basically had hydrogen and helium. It took time for the material to cook in the center of a star, explode its guts, and make new stars that we are actually made of. So that took some time. So very early on, it was mainly hydrogen and helium. So what happens in this very early galaxy, you have a cloud of gas and dust. Again, it's mainly hydrogen. Something happens in that galaxy. Maybe there's an interaction in the cloud, or maybe there's a really hot star that sends some very high energy radiation, and something happens to one of the individual atoms. You take a hydrogen atom, and it gets excited. It hits something else, or a photon hits it, and the electron in that hydrogen atom gets sent up into a higher energy orbit. So it gets into a higher orbit. And in a very short time later, that photon will fall back down to the ground state. And I think, as we all know, conservation of energy, and I think we probably all understand this from high school chemistry and physics, that once that electron falls back down, it emits a photon. Okay? Now that photon is free. Okay, so that photon 10 billion years ago then starts to travel outside of the galaxy. It starts to travel, and as it's traveling through the universe, stuff is happening to the universe. There may be a mass concentration. That photon will bend around that mass. And so the path of that photon includes information of what was behind it, of what it went through. As the universe evolves, it's expanding. And so as the universe is expanding, that photon from 10 billion years ago is actually expanding its wavelength as well. So in the wavelength of the photon is partly encoded the expansion history of the universe. Okay, so that photon traveling for 10 billion years in our time. In the photon's time, there's no time at all. It's instantaneous. For a photon, it sees the whole universe at once, which is at all times, which is pretty awesome. So the photon is traveling. It's traveling through space, and it sees, oh, well, there's the Milky Way. It's going towards the Milky Way, and then it sees the sun, and then it sees this blue dot called the Earth, and it says, oh no, what's going on here? And it's going towards the Earth, and then it goes towards West Texas, and it hits that primary mirror. It's been traveling for 10 billion years, and it hits that big mirror, and then the last very small time of its life, it hits that primary mirror, it bounces up into all the optics, it does like a ping pong back and forth, and then it sees this, and it says, oh crap, what's next? So it sees this image here, and what this image is, if I just do a zoom in, where's my laser pointer? It's the red one. Yes. So what these are optical fibers. Each dot there, it's a rod of glass. When a photon hits that rod of glass, then we can change its path, and we can bend its path. You probably all seen optical fibers. That's how a lot of the communication goes. Each little box here is one of these boxes here. We have filled, this is the focal plane of the telescope. This is the full focal plane. We have filled the focal plane of the telescope with these tiny, tiny optical fibers. What we're trying to do is we're trying to capture every one of those photons. And so it goes into one of the fibers, and this grid here now is by far, it's a factor of 3 larger than any other spectrograph on the planet. And you see these holes here? These have yet to be filled. We're filling them probably in a month to 2 months' time. Every time we get a new object in here, I get like super jacked excited. This is where our data is. This is the essence of what we're doing here. Is we're trying to collect the photons. That one photon hits in here, and then it goes down there. And as soon as it goes into that optical fiber, then we can take that path of the fiber. That path of the photon, and we can have it go into a spectrograph. Once it goes into the spectrograph, then we can take its light, and we can have the blue photons go one way and the red photons go the other way, and then we can tell what the velocity is of that object that emitted that photon. That's the whole idea here, is to take that. And so how that photon ends, it sees this, and then it goes for a little bit of a ride down this optical fiber, and then it hits a CCD detector. That's the same thing that's in your cell phone. And what happens there, it hits some element in that detector, knocks, and now this is where the photon ends its existence, knocks off an electron, and then that electron, we can capture that electron. We can turn that electron into a signal with an A to D converter, an analog to digital converter, and then we can record it, and then what we do is we turn it into the next phenomenal eye candy, which is this one right here. What this is one optical fiber here. There's another one, another one, another one, another one. I have 35,000 of these. Here's another one, here's another one. So what this is here's the blue light over here, the red light over here. And this is what we see. The problem is what we see here, these are photons. So not all photons are equal. These photons suck. These photons are the ones that are coming from the sun. Even though McDonald Observatory is one of the darkest sites in the world, we're still getting scattered light from the sun. So we are dominated by the sunlight. And what we have to do is subtract that off. And so what I do all day long is I write computer code to subtract this off and turn this image, into this image over here. And that's what I want to do. I want to get rid of those 8-minute-old photons. Those are no good. Those are the ones coming from the sun. And I want to try to find the 10 billion-year-old photons. Those are the ones that matter for me. And so what we have here now is an example of the photons I'm looking for. There's one there, one there, one there. This is about 11 billion years old. This is about 10. This is about 9.5. So just a question, how do I know the ages of these photons here? By the wavelength, by the redshift. The ones that are, so this is the red part of the spectrum, this is the blue. These are more shifted to the red, and so I can I know what my range is, and so these left the galaxy 11 billion years ago. So this is what I do every single day, mainly in the morning, is I look at hundreds of galaxies which no one has seen before. And that always blows me away when I do that, and I don't get a lot of sleep, but it's still a lot of fun. So what we do, why this works, is we want to, what we want to do is we want to measure exactly, precisely where that was. It's not only enough to say, oh, it's about 11. We want to know to very high precision, because then what we're going to do is we're going to take that distance, that 11 billion years, and turn it into a map. Okay, and now we get to so this is the hard part, trying to make this data as uniform as possible. And now we get to the easy part, and that's this right here, which you're going to have to memorize this equation. And if you ask a question, I'm going to ask you about this equation here. So what we're trying to do is we're trying to understand the expansion of the universe. And what I just showed you is the fundamental, the essence of the data that what we do. And what we're doing is we're making a catalog. And what we're going to do with that catalog is we're going to make a map of the universe. And from that map, we're going to try to understand the expansion of the universe. And let me explain how that goes. This equation is what underlies the expansion of the universe. And we don't need to know all the terms, but just let me talk about a few. On the left side is the observations. That's the expansion rate. We can relatively easy figure out the expansion rate. It's just a simple measurement. If you know how far away an object is and how fast it's moving, that's a rate. If you do that at another distance and you get that velocity, and you go on and on and on, you can trace out the expansion history. It's like if you had to, make a model of a bomb. What you would do if you can measure every particle's position and every particle's velocity, you get the expansion rate of that bomb. So that's much like what we're doing here is we're going to measure where objects are, how fast they're moving. Okay, so these are the observations over here, and then on the right is the theory. And just let me place this in context in a relatively short time. The theory is you use what's in the universe and you use our knowledge for how that material evolves. We know that there is radiation in the universe. There are photons. We know there's matter in the universe. That's the stuff that we are made of. That includes normal matter and dark matter. There's the shape of the universe, whether the shortest distance between 2 points is a straight line or not, but that's a minor component. And let me get to this term in a moment. So back 15, 20 years ago, and I think you've probably heard this story, when we did this first measurement, we had the observations for how much the universe is expanding. We had what was in the universe, radiation and matter, and we did the calculation. We had the theorists tell us how much radiation and matter should be there, and we had the observations for how much the universe is expanding. And what happened is that this side didn't equal this side. The observations, when you did the calculation, you were 3 times higher on the left side than on the right side. So we did so after a collective in the community, we did what every good graduate student or undergrad would do, is we added in a term and figured no one would see it. Well, let's put this term over in there. Let's give it a really fancy name. Let's call it a dark energy. Ooh, that sounds cool. And let's pretend we have a problem there, and this is what it is. And so what dark energy is, and what I've always said, is it may not be dark, it may not be energy. It's the phrase we use to represent our ignorance of what's going on in the universe. And it is 75% of the universe is in this ignorance term. And that's remarkable. I mean, it's kind of a job security, but it's still kind of remarkable that we don't know that. And so what HETDEX is trying to do, and so that's why that individual photon is so important. What is it? How does it go? Every photon is sacred, every photon is great, if just one photon, sorry. And so what we do is we take those photons and we have them at different timestamps in the universe. 7 billion, 8 billion, 9 billion, 10, 11. And we're going to make a map of the universe, and we're basically are going to see how that map expands over time. The important point is that when the galaxies are distributed in the universe, they're distributed in a set pattern. They're not completely random. There is a pattern underneath there. So what the whole point of HETDEX is trying to pull out that pattern from a giant map, and then you can see how that pattern is expanding. And then what we're going to make this measure. I did this again. What we're going to do is make this measurement very accurate. We're going to make as precise a measurement as ever been made in terms of how much the universe is expanding. And then we leave it to the theorist. Now, the theorists have let me down so many times. They missed this term over here. It's kind of embarrassing, but I'll give them one more shot. And so that's the essence of HETDEX of right now. And this is the cartoon. So just to put it in big context as well, down on the bottom is the Big Bang. This is when the universe was all in a very small spot. And you can think of the time axis as going this way. And what happens is the universe is expanding. And it's expanding because of the Big Bang, because so very early on there was a bang. We don't quite understand what caused the bang, but we know there was a bang. And it expands out. And As the universe expands, then the mutual gravitational attraction of stuff in the universe will cause the expansion to slow down. And the example I like to use is if we took all of you, placed you out in space, we can put spacesuits on, and then just let you go, you would slowly come together in one giant human blob, very unhappy human blob, but you would come together into this human blob. And that's because of gravity. And so as the universe expands, you should slow down in that expansion, but the observations show at some point something happened, that something is our ignorance of dark energy, and it's expanding out. And so that's the idea for what we're trying to do in HETDEX. And this is some data. Here's some galaxy here. So what I do is I look for dots. I write code. I look for dots here. Here's an obvious one. Your eye can find that. But all I do is I search these things very, very, very intensely for dots. And that's what I've turned into right now, a dot finder. And I'm going to show you a few dots, okay? And this is what we're after. We need a few million of these dots. So here's a few. Here's a galaxy that is, here's some dots up here. These are beautiful dots up here. These are very bright. This is a galaxy that is probably only 8 billion years, that its light left 8 billion years ago. Since I spend my whole life doing this, I'm going to show you a few more. I have about 10,000 of these right now. Here's another one. This galaxy is a nearby galaxy. So this is not our data. Then we go and we try to see if anyone has taken an image of it. Here's a galaxy. So this is a nearby galaxy. This is only about, these photons are only about 3 billion light years old, so I don't really care about those. Here is another beautiful one. Here's another beautiful one. And that's where we are. So right now, I'm just trying to make a catalog. We're up to about 10,000. We have produced 20 million spectra right now. I know there's a couple of grad students and undergrads who are trying to go through those spectra, I hope right now. Even if they're here, I don't care. And the idea is to catalog this. We're starting to take our observations in full right now. We're trying to go a full bore. And as I said, it should be about a 4-year survey. And just again, to say what the essence of HETDEX is, we're going to make this map. And here's an image, a computer simulation for how the galaxies are distributed in the universe. And we can pull out a very faint pattern in here, and we're looking for that pattern. So that's it. So it's much like when the galaxies are distributed in our universe, there is like a fingerprint. And as the universe expands, that fingerprint expands. A nice analogy is you. If we were able to take your fingerprint, and since you were a baby until now, if we measured the actual space in millimeters in between the ridges of your fingerprint, we would get your expansion rate as a function of time. Those of you who are drinking beer, it may be a little bit higher right now and might get a little smaller, but that's the expansion rate. That's a very close analogy to what we are doing. We're just trying to measure the distance between these ridge lines and then tie that back into a model of dark energy. Okay, so what can HETDEX do for you? So this is a survey that is after a dark energy and the expansion of the universe. But this is a survey which we have not done yet in astronomy. It's the essence of discovery. We are looking at the universe. We're taking spectra of the largest swath of sky that has ever been done with the largest telescope. And there is a litany of science that are going to come out of it, from how our galaxy formed, how the Milky Way formed, to the most massive black holes in the universe. And so there is just a pile of science in there. This is what I love. This is just, I mean, it really is. Searching through this data that no one has done before is just, it's fantastic. Okay, so I will end there. So thank you very much.
All right, thank you all about nothing. We got time for a couple questions. All right, first hand I saw in the back.
So no one yet has observed dark matter, as I understand it. Is that accurate? No one has observed a dark matter or a dark energy. So this is a dark energy, but a dark matter is, it's another thing we don't understand. How is this different from ether? Yeah. I don't know. Okay, so that's a great question. That like back in the 1900s, there was the idea of the ether. One of the best interpretations that I think most people subscribe to is that a dark energy is a product of space itself. That space and just like we heard in the previous talk, space now has it's a physical entity, right? We can now feel space. We can interact with that space. The stuff between you and I, it's not just empty vacuum. It's like a three-dimensional, four-dimensional, when you include a time of a piece of graph paper. So that is an entity. If that stuff has energy associated to it, that could be the explanation for what a dark energy is. That would be similar to ether in terms of the physics behind it. It's a different beast, but the concept itself is very similar. Yeah, there are, I don't know if I have all that, but there are some crazy ideas out there up top of here for, we live in a four-dimensional universe. We believe that we exist in a 10-dimensional universe. If there's interaction between the dimensions, then yes, it could explain, it could have an effect in our universe. I have ideas of dark energy on the left here, the standard ones. And the ones on the right are the ones when you're in a Colorado or Washington and you buy some legal weed and you start talking about what is going on over there. And that's one of them. But it's so exciting now. I mean, it's a theorist gone wild type stuff. And it's so exciting now that you can't, I can't say no. I can't say that's not what's happening. That's partly what I want to do with HETDEX is really nail down what that expansion rate is and tie it into those types of models.
All right, one more question right there.
So our code is written in Python, C++, a little bit of Perl, Bash script, and I write in Fortran because I'm old. And the Fortran code is the fastest by far. So.
All right, and a shout out to Fortran. Let's end there. Let's thank All About Nothing one more time.
That's great, Karl. Thank you.